Hi there. In this video, we're going to talk about setting up hypothesis tests for two parameters, and we're going to be using simulation to do this. So let's do a little recap and where we're going in the first part of this video. So we're testing, in this class, we're testing hypotheses in 5 different scenarios. Okay, so we've looked at one parameter in 3 cases, and these first 2 are very similar because they both use P. But we've looked at something where there's a process probability, and that's a proportion, so that's a lot of P's there. And then we've also looked at something that's a sample proportion coming from a sample. And then we also looked at means, okay? So corresponding to that, we've looked at these 3, actually we used these 2 because we use proportions for both of these P ones. Okay, so now we're going to go forward and look at 2 parameters, okay? So in our case, this will always be a difference. So a difference of 2 proportions or a difference of 2 means, okay? And you can see those are the next 2 on our stat key applets on that website. And then in this class, we won't do slope testing for slope or correlation. That's really cool too. That'll be in a future class like Stat 244, or maybe a different class if you take more stats classes. Okay, now these differences are so cool because now we get to get into testing results from experiments and things like that. So this, using simulation for this allows us to do things that we wouldn't be able to do because we won't have enough time to cover the theory, but because of simulation, we'll be able to do that in this class, okay? The theory is really interesting too, and that will be also in Math 244, or Stat 244 if you take that, or another future stats class that you take. Okay, so we're going to get to do that today, though, which is just really exciting to me. Okay, one note I want to make about the difference of 2 groups. So remember, we're going to be looking at either 2 proportions, so for that will be P, or 2 means, and that will be mu. We're going to be looking at the difference of 2 groups. Now there's different ways of using 2 parameters, right? So if we had, say, a before and after, the same group before and after, that's called a matched pair because it's the same person, but it's before and after, or the same group before and after. That's a different theory. We're not going to use that in this class, but it's also another really interesting case to look at. But there's less variability in that case versus if you have 2 completely different groups. So it's a little bit different situation. Okay, so we're going to be looking at the difference of 2 groups in both cases, okay? 2 different groups of people. So this is perfect for experiments because it's like a control group and a treatment group. Okay, so let's get into one of these. I've got a hypothesis test for 2 parameters here. Beer and mosquitoes. So does drinking beer attract mosquitoes? That is the question. And I've got the study referenced here, and it's linked in D2L if you want to read more about it. It's a really interesting experiment that they did. Okay, and it was done in Burkina Faso, Africa, because there's malaria, and sort of with the rise of industrialization there, alcohol consumption has increased. And so this study was done to try to, first of all, see if there's a significant attraction from beer more than water, and then to do public service, public education about this. Okay, so as far as the experiment, 25 volunteers consumed a liter of beer, and 18 volunteers consumed a liter of water, okay? The volunteers were assigned to the 2 groups randomly. We have to have random assignment, right? We've learned that about experiments. So this is after they drank the beer or water. Mosquitoes were released and caught in traps as they approached the volunteers. And they have built some special contraptions to do this, which is in the article, so I hope you take a look at it. For each group, the number of mosquitoes caught per person. Okay, so I want to underline this because this sounds like units, right? The number of mosquitoes caught per person is listed below. Test the claim. Okay, so this is going to be our alternate, right? Test the claim that the beer drinkers attracted more mosquitoes than the water group after the drinking. Okay, and then here's our data right here. So the beer drinkers, I don't know, I'd have to read the study again to see how long this was, but the beer drinkers, you can see they attracted one person 27 mosquitoes, one person 20, 21, and so forth. And then the water drinkers, 21, 22, 15, and so on. So there was a lot of mosquitoes in general right here. Okay. So let's look at what we're going to write here. What's the parameter of interest and what's the direction of the test? Okay, so we're going to use this to write the hypotheses. Okay, I've got a graph here I don't want to show you quite yet, but I will in just a second. First, because we don't have this when we're thinking about what our parameters are and what our hypotheses are, okay? So parameter of interest, we need to be thinking are these two means or two proportions? We do also, they'll be mixed up later on. So it's like, is this one thing or two things? This is two. We have two groups. And are they going to be means or proportions? See if you can answer that. Okay, if you said means, you're right, because these are numerical variables, right? So I'm going to write that over here, numerical variables. So we're going to use means. Okay. So we're going to write our hypotheses. So think about this. Let's say we have a mu for the beer drinkers and a mu for the water drinkers, right? So those are going to be our parameters. And then we'll get to the statistics in a minute as well, right? Okay, so the parameters for the null, well, the way we set up the null in a comparison of two groups is that there's no difference between the groups. There's no difference between drinking beer and water in terms of attraction of mosquitoes. Okay, so I'm going to write that they're equal to each other. Mu for the beer is equal to mu for the water. Okay, and that is our null hypothesis. Now, we could also write it, you might see it another way, so let me write that as well. You might see it as a subtraction, or mu beer minus mu water equals 0. Okay, that's another way of saying there's no difference. So these two are used pretty interchangeably, so you could use either one of those. Okay. So that's our null. We still need to write our alternate, right? So our alternate, that comes from, it says, let me move this up. It says test the claim, right? The alternate comes from our claim. Beer drinkers attracted more than the water group. So that's going to be mu B is greater than mu water. Okay, really important to use the letters that correspond to the study because it can get really confusing if you don't. If you use 1 and 2, you're like, wait, which was which again? And the order does matter here, right? Because the beer has to be greater than the water. So if we rewrote that one as a subtraction, that one would be mu B minus mu W is greater than 0. So if we have a positive difference, so this order does matter, right? If we have a positive difference, the beer is greater than the water, the number of mosquitoes. If we had a negative difference, the number of mosquitoes attracted by the water drinkers would be more than the beer drinkers, okay? So we're testing that the beer is more than the water. Beer attracts more mosquitoes than water. Okay, great. So now letter B here says, using an appropriate randomization test applet, select the data set and simulate the randomization distribution. Okay, just like we've been doing. So let me go over to our stat key apps. These are on the right column. These are our randomization hypothesis tests. So we've used mean and proportion. We also saw the Rossmann chance for proportion. You can choose between those two. For that one, and then difference in means or difference in proportions. So we need to go to difference in means, okay? And you see a little graph, kind of like we've seen before, of the original sample. And so we need to choose our data sets, okay? Or we could also input something. We do have the data here. We could input it. But this one is also in one of these data sets. So I'm going to look for mosquitoes, beer versus water. It's about halfway down. And click on that. Okay, so let me explain what this is. So on our notes, we had a list of numbers for each group, right? Each one of those is a little dot. You can see water, the lowest is 12, 13, 215, 16, etc. And we have the sample mean. Whoops, when I hover over it, it disappears. We have the sample mean right there, 19.222 mosquitoes, right? And that's the top part of the graph. The second part of the graph, we also have the beer drinkers. You can see the smallest there was 17, and then 18, 19, 19, 20, and those go up to 31. Okay, so it does look like if we just compare these two dot plots, also the mean for the beer drinkers was 23.6 mosquitoes. So if we compare these two dot plots, it does look in general like the beer drinkers attracted more mosquitoes. However, what we're testing is that just due to chance, or was it really the beer, okay? Is it just these folks attract more? I tend to attract a lot of mosquitoes, even when I'm not drinking beer. So is it just the person-to-person difference? Or is there a significant effect of the beer? That's what this experiment is testing, right? And we can conclude causation here if it's significant because they've used random assignment. They've separated, they've sorted out, split up all the other possible variables, right? But we still need to know, is this difference significant or not, right? Okay, so let's see what else we have on here. We have our two sample means, and then under the original sample here, it says x bar 1 minus x bar 2 equals 4.38. N1 is 25 and N2 is 18. Now, remember how I was saying it's important to use the letters for the groups? This app doesn't do that because it doesn't change its notation based on the data set. So we need to figure out which is which and then make sure we know which is which. So one thing that's really handy is if the sample sizes are different. And one is 25, and we had 25 beer drinkers. So that's really handy. And then N2 is 18, and we had 18 water drinkers. So the 1 is on the bottom, and the 2 is on the top. So I'm going to go back to the notes for a second, and I'm going to write down, I'm going to write under here the x bar 1, I'm just going to put a B there and a W. It's kind of small, so I don't have room to put x bar B and x bar W, but I just want to remind myself that it's beer minus water. And that also, not too coincidentally, but that also matches up with the direction of our test, right? We're testing that beer is greater than water, so we want to do beer minus water. Okay. Another way to tell, and we'll get to the sample statistic in a moment, but another way to tell is whether the difference is positive or negative, right? So if I just go ahead and write x bar B minus x bar water, actually let's just go ahead and do it. These are our sample statistics, right? So we have the sample average or sample mean for the beer drinkers minus the sample mean for the water drinkers. This is our statistic that matches with our parameter here, right? And they're doing the subtraction because we need to find out if that's the math we need to do, right? So that is equal to 23.6 minus 19.222, and that should equal, if we have the order correct, that should equal 4.38, right? 23.6 minus 19.222 is 4.378, and they put 4.38. Okay, so they rounded to 2 digits there. I'm going to write equals 4.378. Okay, what are the units on that? If you said mosquitoes, you're right. Okay, I always want to add the units as well. Remember, that helps us remember what we're doing and helps other people know what we're doing. Okay, so this is our sample statistic. So on average, the beer drinkers did attract a little more than 4, between 4 and 5, but closer to 4 and some mosquitoes per person more than the water group. Okay, that seems like something, but we still don't know if that's a significant difference or not yet, right? Okay, so I did that partly because we'll need this in our test, right? This is our sample statistic, or in a test we often call that the observed statistic. Let me write that down. Our observed statistic. And I did that also to double check that this difference was correct, that it was in fact beer minus water. Okay, I would definitely need to do that if my 2 sample sizes were the same and I couldn't tell any other way, right? Okay, well, let me get my next page here. And we're going to go, it says, there's the link to the article, and I put it in D2L for you as well. Use the randomization distribution to find an approximate p-value and insert an image. Okay, remember it says approximate p-value because we're doing a simulation. Versus theory, okay? Okay, let's go back to the applet and I can explain what this is doing. Okay, so we've seen before that our null hypothesis is there's no effect. So the null hypothesis here, they have written it here, is mu1 equals mu2, or mu beer equals mu water. Okay, so if there really is no effect, then these, what's 25 plus 18? These 43 people could have been in either group, right? And then if there really is no effect at all, then these 43 people could have been in either group. So what we do is we just reshuffle the groups. It's called reallocating the groups. You'll notice there's some different randomization methods here. We're going to mostly just use reallocating the groups. So imagine if we had cards, a deck of cards, and we had 43 cards, and we had the average we had the number of mosquitoes for each person, and then we just shuffle them up, and then we deal 25 in the beer group and 18 in the water group, and then we count them, then we average the mosquitoes, okay? That's in each group. That's what this simulation is doing. So I'm going to do a few slowly so you can get an idea of what's happening here. Okay, so I'm going to generate one sample. Okay, so what it did was it reshuffled. It took all the 43 people, shuffled them together, and like randomly assigned them. So they were randomly assigned before the experiment, but now that we have the results, we're randomly assigning them, okay? And in this case, the water average was actually higher than the beer average, okay? So remember, we're setting up our randomization distribution on the assumption that the null is true, that there's no difference between the groups, okay? Then we'll test and see how strong our evidence is. Okay, so you can see the different allocation, the new random assignment, and then they subtract, and it came out negative this time because the beer was actually less than the water. So you'll see null equals 0, and we have 0 in the middle of our graph. So in this one, we'll be getting negatives and positives. Let's do another sample. Okay, so now the beer is slightly higher than the water, and they just reshuffled the 43 people into a group of 25 and a group of 18. Okay, I'll do that again. Bear is slightly higher. So you can see the difference here is 1.22 mosquitoes. So that's this dot right here, a little over 1 mosquito per person. Okay, do another one. Do a few more. So each time we're just randomly reassigning the people, okay, into different groups, into the two groups. Okay, now what do you think is going to happen if I do 2,000 of these? What is the shape of our randomization distribution going to look like? I almost made it with my hands. If you guessed that it's going to look like a normal curve, you're right. It looks like a normal curve. And that's because the values in the center are more likely to happen and the values on the edges are less likely to happen. Okay, so this is our randomization distribution. Okay, and I have a picture of this on your notes. Of course, it's a slightly different one because it's from a different simulation. Now, let's see. Do I want to go back to the notes yet? Not yet. I think I'll just read off of there. It says the next part is compare the p-value. Oh, sorry, I didn't finish C. Use the randomization distribution to find an approximate p-value and insert an image. Okay, so we're up to the p-value part now. So that's, remember, here's our original sample, and the difference was 4.38 mosquitoes, okay? So we want to know how likely, with all this random assignment, reallocating of groups, how likely is it, if the null is true and there's actually no difference, how likely is it that we got a difference of 4.38 mosquitoes? Or more precisely, 4.378. We'll see if there's a difference in the p-value there. Okay, so this is a right tail test because it's a greater than. So I'm going to click on right tail. And remember, this always comes up with 0.025 to start with. That's not necessarily our p-value. We need to go in. We can see that does correspond with 2.658 mosquitoes. But we need to put in our original sample statistic, which is 4.38. That's what the computer's saying. 4.38 mosquitoes, and it's way over here. You can see it's over, what's our standard error? Okay, these aren't standard errors, so I don't know exactly. It's quite a bit a ways from, I was going to try to say how many standard deviations away is it, but we don't know that for sure. But it's pretty far away because there's a 0 chance. We didn't get that happening in any of our samples, okay? Now, could it happen in another simulation? Sure. Maybe we get 1 or 2 out of 2,000. Still going to be a very, very small chance, right? So our p-value is actually 0 in this case. Now, I just also wanted to change it to 4.378 was with the 3 digits, and that's slightly smaller, but we still didn't have any that were that high. Okay, so it looks like this is a very significant result, because if we had, say, it was just due to individual differences, if we reshuffled them 1,000, 2,000 times, we did it 2,000 times, we never got a difference of more than 4 mosquitoes, okay? Yeah, you can see there's nothing above 4. 3 point something is the highest that we got. Okay, so this is a significant result. Okay, so let's go back to our notes for a second here, where I have captured this for you. Okay, and I'm going to write, here's the question right here. So I'm going to write the p-value that we got. And you can see I did a different simulation before to print out in the notes. And in that simulation, it looks like possibly 1 was above. And so the p-value is 0.0, it's too small, 0.0005. Very, very small, right? So I got 2 different p-values. P-value equals 0 in one simulation, and I'm also going to circle it right here so you know p-value, that's the p-value, 0.005. So that was a different one. Okay, these are both very, very strong evidence, right? Very significant. Okay, great. So there is the distribution, and you can see here I put in the 4.38. So this is our observed statistic, which I'm going to circle right here. So we put this number right there, and we get out the p-value. So we put the original sample into the right, when we click on right tail, and then we put the observed statistic along the x-axis or horizontal axis, and then we get out our p-value. Okay. Another interesting thing is if you want to see exactly how the each sample went, you can show data table under here and get that as well if you're interested. Okay, hope it's making sense so far. Let's go ahead. We've done these. By the way, I copied this ABCDE, same steps that we were using before, and then eventually we'll take those training wheels away again. And it's slightly different for whether, how you interact with the app, because if it's one parameter or two parameters, they're slightly different. Compare the p-value with the significance level alpha and determine whether the result is statistically significant. Okay, now I'm going to go back and see, was there an alpha given? I don't remember one. It doesn't say test at the blank blank level, right? So we're going to use 0.05. That's the most common level used. Alpha equals 0.05 unless specified otherwise. Okay, so our p-value, and I could use either one that I got, right? And you would get a different one as well, likely. So I'm going to use the one that's printed on the notes. P-value equals 0.0005, or you could use the largest one, right? Because that's the worst case, but I'm expecting these to vary. Is less than 0.05. It's much less. So this is strong evidence. So this result, this is statistically significant. Okay, and then we get to state our conclusion. And we always need to put the context in our conclusion and the p-value and whether we reject the null or fail to reject the null. Okay, so lots of different ways to write it out, as long as you get all the key information in there. So I'm going to write with a p-value of 0.0005, there is strong evidence that there is a difference. I'm going to say significant difference. Okay, so this is where I have to put in the context, right? So feel free to always go back and read again if you need to read the context. There's a significant difference between, or actually, I don't want to say it that way. Remember, you always want to go back to the claim, right? So there's significant evidence that the beer drinkers attracted more mosquitoes than the water drinkers. Okay, so let me change this a little bit. There's strong evidence that the beer drinkers attracted more mosquitoes than the water drinkers. And then I'll say because we have a very small p-value that's significant, that means we reject the null hypothesis. Okay, I could have put that in a different order. I could have said with a p-value of 0.0005, we reject the null hypothesis. There is strong evidence that beer drinkers attracted more mosquitoes than the water drinkers. Okay, so anything along those lines. Perfect. Well, let's do another test in the next video, and I'll see you there.